So, we continue our discussion on arriving at the momentum conservation equation. So, our starting point would be what we have seen so far, which is that the conservation of momentum in a fluid can be expressed as the density times the acceleration being balanced by the divergence of the surface stress, and if there were any body forces, then you would have the body force per unit volume that would act in the problem. So, an example of body force that I keep giving would be gravity, the weight of the particle, the weight per of the fluid parcel rather per unit volume. Now, we saw that sigma ij, which is the stress tensor, we can write it in terms of a contribution that you would experience if the fluid was in a static state. So, if you have a static blob of fluid, which is have some density, then at any point in the fluid, you would have a pressure that would force that would act in the problem. So, in a hydrostatic configuration, the balance that would occur would be a balance that would be between the pressure forces and that of the body force. So, you would have, if I define this as my z direction, I would have an equation which would be minus dou p dou z, which is the pressure gradient in the vertical direction, that is balanced by minus rho g. Or if you write it in a vectorial form, that will be minus gradient of p plus whatever is your body force. So, if you write that too in a vectorial form, this is what it would be. So, this is an equation of force balance for a fluid which is in static state, a hydrostatic scenario. So, what we are saying right now, that the total stress that is acting in the system will have a contribution that comes from pressure and a part that is due to the motion, which we are calling as a viscous part. We will soon basically label what that viscosity actually is, but there is an additional part that is due to the motion that is occurring in the problem. Now, obviously, when there is going to be motion, the pressure, what we are calling here as the pressure, is also going to change. The pressure in a fluid in its static state and in a state of motion is not the same. But we are doing this kind of a splitting so as to we know a part that we are already familiar with from hydrostatics. And this is where we had this point that we made, that the pressure that we are writing here, we still continue to call this as a thermodynamic quantity even though the system is not in equilibrium. There are fluxes that would be there would be a mass flux, there would be a momentum flux in the problem. So, if I were to design any region and I actually try to measure the mass flux and momentum flux, there is stuff coming in, stuff going out. So, strictly in that sense it is not in equilibrium. But if you are interested in liquids that or fluids that we have in mind, let us say something like water, you can work out what would be the relaxation time scale for water molecules, and those would be practically 0 on the scale of observations that we are making. So, on the time scale of flow observations, you would not really be considering any relaxation for these things, you will think of them as instantaneously relaxing, which is why we are going ahead with this statement that P that we have here continues to be, we are assuming, and a reasonably good assumption, assuming it to be thermodynamic pressure. Deviations will obviously occur, as you can now see that you can always work out a counter example where this will fail if you are thinking of scenarios or thinking of fluids where the relaxation is not so small. Once the relaxation becomes of the order of few milliseconds, which will happen when you have a fluid that is made up of, let us say, polymer molecules. So, if you have a fluid which is now made up of long chain polymer molecules, the relaxation time scale of these polymer molecules will depend on the molecular weight of these polymers. So, if you have large chain polymer molecules, the relaxation time scale can be quite large. that you stretch them, you leave it, how long does it take for it to relax? So, that is the concept of relaxation when the fluid is made up of something other than what you are thinking of as just billiard balls. So, in which case relaxation time scale can start to approach fairly large values, large with respect to what we understand for fluids like water like systems. So, in which case if the relaxation time scale starts going towards few milliseconds or even higher, then the consideration of thinking of the system being in thermodynamic equilibrium gets a bit dodgy. But we are going to proceed with only thinking of fluids which are more conventional in terms of how we are designing it. So, fluids which are water like systems. Okay. So, with that what we saw that the next assumption that we made was that of a Newtonian fluid, and for a Newtonian fluid we said the assumption was that this additional contribution to the stress depends linearly on the velocity gradient. And to be tensorially consistent, we realize that this relationship which of linearity will have a constant of proportionality, that is a fourth order tensor. So, the Newtonian fluid is where we are doing a linear constitutive model. So, that automatically tells you that whenever you hear about non-Newtonian effects, so when you read more about fluid mechanics, when you read more research papers on fluid mechanics, when you come across people discussing about fluids and you hear the terminology non-Newtonian fluids, the first thing that you would realize that the linear relationship between stress and the rate of deformation is no longer applicable for such scenarios. You are going to have something that is non-linear. What exact form? That depends on case to case basis, but the Newtonianness of the constitutive relation basically just says that the stress tensor is linearly proportional to your deformation gradient. And then we use 2 points, one was that of isotropy and the other was that of symmetricity of the stress tensor. So, this was isotropy of the medium, and the next was the fact that the medium does not have any body couple, which is why you have the stress tensor being symmetric. With these assumptions, what we arrived at was that finally sigma ij with the substitution of what should be an isotropic fourth order tensor. So, the general form of an isotropic fourth order tensor would be expressed in terms of second order isotropic tensors like delta I, combinations of delta ij, delta mn, delta im, delta jn and delta in, delta jm. So, we have linear combinations of these, and then after doing the linear combinations and using the symmetricity, we finally arrive at the fact that your stress tensor, what we wrote down in the last expression, was proportional to the rate of strain tensor. So, we had sigma ij was A delta ij. So, this is the part which is viscous, as we will write down quickly, and then the next part was 2B Eij. So, your total stress tensor is minus P delta Ij A delta Ij EMM plus 2B Eij. Now, these constants which are appearing in relating the stress tensor with the rate of deformation, these are transport coefficients. They are coefficients which basically tells us that what is the response of the system to motion, and this appears in various branches of physics. If you are trying to basically understand that given there is a temperature gradient, what would be the heat flux? So, you would need a transport coefficient for that. given that basically there is an applied electric field, what would be the displacement field? That would be the dielectric constant. So, there are various transport coefficients which continuously appear in various branches of physics. So, this is our encounter of what we have, and now we will give traditional names for this. So, I will use notations that we are all familiar with. I do not want to introduce something new here. This is the coefficient of dynamic viscosity, mu, and lambda is the second coefficient of dynamic viscosity. As you can see, the units, if you just want to first work out what would be the units, sigma has dimensions of Newton per meter square. That is the dimension for the stress. E, or the rate of strain tensor, has units of second inverse. Its velocity gradient, so thus it will have units of inverse time scale, which means your dynamic viscosity has units of Newton second meter to the power minus 2. If you write it in more traditional notation of MLT, mass length time, this would be mass length inverse time inverse. Newton will be written in terms of mass length and time, and so you finally will have that. This small point will come back again because we will encounter another kind of viscosity, which is why I just want you to pay attention to the fact that the dynamic viscosity has dimensions that involve mass in it. So, this is what is the constitutive relation between stress and the rate of deformation in a Newtonian fluid. So, this is quite different from a conservation law. This is constitutive modeling. As you saw, that various steps we made assumptions when we arrived at this. This is not something being done from first principles. You make certain assumptions of the material. So, what assumptions have you made? Your first thing that you have assumed is that there is a linear response in the system. There is a linear material in terms of its constitutive relation. Now, how do you validate this? One obvious validation, which is how these theories have developed, is from experiments. You perform experiments and you try to actually see that what kind of a stress does the system develop, given that you apply some kind of a velocity gradient or some kind of a straining in the problem. Just like how you do a spring experiment, right? That you have a spring and you basically find out what is the force. If you stretch the spring, what is the force that is you are experiencing from the spring? And you find that there is a linear relationship between force and the stretch or the compression of the spring, and that gives you the point of a Hookean spring. So, that is the approach which you have done earlier for problems of stretching or compression. You are exactly making that kind of an approximation or making that kind of an assumption for the system. And as I already went through this is a very good assumption for systems which are water-like. And now you know what do you mean by water-like. By water-like, I am basically trying to say that the relaxation time scale that is actually there in the undergoing fluid is very small. So, if I write down a relaxation time scale for the underlying microstructure, the word underlying microstructure means what makes up that fluid. Is it made up of water molecules or is it made up of something else? So, if this underlying relaxation time scale is significantly smaller than a flow time scale, it is reasonably good to approximate the system as a Newtonian fluid. So, nothing is perfectly Newtonian. Newtonian is an assumption regarding the constant relation of a fluid. Everything will have some kind of a non-Newtonian nature. This was again going back to what we discussed probably in the initial lectures, that a fluid will have an elastic response in some regimes and a fluid-like response. So, every material will basically go from a solid to a fluid response. And now we are giving some precise meaning to this statement. So, instead of having a bunch of water molecules, if you have a bunch of polymer chains which make up your fluid, in the case of polymer chains, you can automatically start to envision that the relaxation time scale will start to increase. You stretch them, you let it go, how long does it take for it to come back to its initial unstretched configuration? So, the relaxation time scale here is definitely going to be much larger than the relaxation time scale that you would have for simple liquids. So, there is a term that is often used called simple liquids in terms of what we are actually doing here, in contrast to what is often known as complex liquids or complex fluids. So, we are dealing with simple liquids. We are dealing with scenarios where the relaxation time scale is significantly smaller than all your flow time scales. Every measurement that you are doing, every sampling that you are doing, every observation that you are doing is significantly larger than the relaxation time scale in that particular scenario, which tells you that if you were to design an experiment or if you were to design a simulation where you were trying to probe the system at very small time scales, or if you are doing this like an oscillation. So, one example where we often do this is you put a material, and I discussed this couple of times so far. You have something known as a rheometer, and this rheometer has a plate that is oscillating with a given frequency. So, if you do these oscillations, when you do high frequency, you are basically sampling the system at very short time scales. So, when omega, which is the frequency, is large, it is expected the system will show more solid or elastic response. Whereas, if you sample the system at small frequencies or large time scales, then you are going to see a liquid or a viscous response. So, everything is capable of showing elastic or viscous response. It always depends on the time scale, because when I say large or small, omega is a dimensional quantity. So, something being large or small is meaningless for a pure dimensional quantity. So, omega when compared with the flow time scale, or in this case it is the relaxation time scale. So, if you do very small frequency oscillations, you are allowing for the system to relax by the time you finish your one time period, that it is so slow that the system can easily relax back, and what you are observing is viscous. So, with all that disclaimers and giving you the background of where we are, because once we agree on the constitutive relation, we can set this up as a mathematical problem, but it is important to pay attention to how we get to this particular place. So, now we have a relation for stress in terms of the rate of strain. So, if I equate I to j, so I get sigma ii. Now, sigma ii is the sum of all the diagonal elements, right. Sigma ii is basically sigma 1 1 plus sigma 2 2 plus sigma 3 3. So, 1/3 sigma ii is an average normal stress. I am using the word normal because you can see that sigma 1 1 gives you a force in the one direction for an area vector pointing in the one direction. Sigma 2 2 is a force that is acting in the two direction for a surface that is pointing in 2, and similarly sigma 3 3. So, sigma 1 1 plus sigma 2 2 plus sigma 3 3 by 3 gives you an average of the total normal stress that is acting in the system. So, this I am going to use a notation which is P tilde, because it is a pressure like quantity. It is not quite yet the pressure, but it is a quantity that is like pressure. So, P tilde is the average normal stress that is acting in the system. So, going back to our expression that we have, sigma ij is minus P delta ij plus lambda delta ij EMM plus 2 mu EIJ. So, if I compute sigma II from this expression, I have minus P delta II plus lambda delta II EMM plus 2 mu EII. All good? Now, we already know, we have done this several times, that delta II is nothing but 3, sum of all the diagonal entries of an identity tensor, and sigma II is, so I will use with the notation minus P. I am using minus P to basically say that if pressure is basically defined as positive, if it is basically acting inwards. So, it is acting inwards. So, the force that comes from pressure will basically be against the normal for a compressive effect. So, we are basically using this convention to say that P tilde basically being positive implies a compressive stress in the problem. So, I have minus sigma II is 3 P delta, and this one becomes minus 3 P. This is 3 lambda EMM plus 2 mu. I can write it as EII or I can write it as EMM. So, I have P minus P tilde is equal to 3 lambda plus 2 mu EMM, or P minus P tilde is lambda plus 2 mu by 3 EMM. So, this, as you can now see, relates to quantities. The P that is appearing here is what we have already said, that we are assuming this to be thermodynamic pressure. Considering that the fact that the system is instantaneously getting equilibrated, or it is a near equilibrium system, whereas P tilde is a mean or an average normal stress that is in a system. So, it is what we will call as a mechanical pressure. Now, you can consider two scenarios. One is when the system is incompressible. If the system is incompressible, which is divergence of u is 0, in terms of rate of strain tensor, this implies EMM is equal to 0. What is EMM? EMM is E11 plus E22 plus E33. What is E11? Dou U1, dou X1, E22 is dou U2, dou X2, E33 is dou U3, dou X3, which is divergence of U. So, when EMM is 0, then P is equal to P tilde, which means you are basically having the mechanical pressure and the thermodynamic pressure being equal, and in your entire problem now you will have the actual value of pressure is not important. What is the precise value of pressure is no longer of any significance. Now, all that you basically will care about is the pressure gradients rather than the precise value, because you have arrived at a relation that your thermodynamic pressure is basically going to be the same as your mechanical pressure, which is nothing but the mean normal stress in the problem. So, the precise value does not matter because the system is driven by gradients in the stress. So, what is your exact value of your thermodynamic pressure is no longer appearing in your calculation, because the thermodynamic pressure is going to be equal to for the so for the incompressible case, you will have, if you are trying to calculate, the thermodynamic pressure basically becomes equal to the mechanical pressure, which is minus 1/3 sigma II. And because what drives the problem is gradients of the stress tensor, which is now related to the mechanical pressure, and thus through that the thermodynamic pressure, there is no significance of the actual value. What if divergence of u wasn't 0? You were dealing with a compressible system. So, when you are dealing with a compressible system, you will have P minus P tilde is lambda plus 2 mu by 3 EMM, and this quantity is known as coefficient of bulk viscosity. Now, coefficient of bulk viscosity, if you start from assuming from the kinetic theory standpoint. So, what is the kinetic theory standpoint? You say that these are bunch of billiard molecules, right, billiard balls which are moving around. So, you have these molecules which are moving around, they are moving around freely in space and then they come and bounce off, and this is all that your system is. If you start from there, from that underlying approach, you will arrive at the fact that you are dealing with, if you are dealing with monoatomic gases, then the coefficient of bulk viscosity would be 0. Now, you can make measurements and you will typically find coefficient of bulk viscosity is not very large, it is quite small. But then when you have gases which are made up of polyatomic molecules, let us say example being oxygen, any diatomic molecule, there is a capacity of rotation that is there the moment you have these two molecules which are present. So, there is no guarantee then that the coefficient of bulk viscosity necessarily should be 0, and there are various ways by which you can check this, and this is something which again is significantly elaborate, that should the coefficient of bulk viscosity be 0. So, typically when we do fluid mechanics for compressible flows, we invoke something which is known as Stokes hypothesis, that says that coefficient of bulk viscosity is 0, which means lambda plus 2 mu by 3 is equal to 0. The consequence being that even if the system is compressible, you still would go ahead by saying that thermodynamic pressure is the same as the mechanical pressure. Now, this, as you can see, is a hypothesis, which means that it is not necessarily something that is rigorously true. And you can come up with examples, you can come up with scenarios where you can show that this is not guaranteed to always be true. And there are a lot of work that has happened to show that this can fail. This can fail in many cases where you are not going to have 0 bulk viscosity. So, in terms of references, some of the earliest work which gives an historical account of all that goes into the bulk viscosity is work by Truesdell. But there is a more recent paper which you should have access to, is by Buresti, which discusses about again the historical aspect of Stokes hypothesis. And obviously, all of this matters when you are talking about a compressible flow. So, we are going to focus only on incompressible flows. So, now we are moving towards writing all of this for an incompressible flow. So, for an incompressible flow, you will have sigma ij is minus P delta ij plus 2 mu Eij. If you remember, the term that was appearing here was lambda delta ij EMM. So, if the flow is incompressible, this term is absent. So, now if you substitute it into your equation, so your equation was rho dou ui dou t plus uj dou ui dou xj is equal to plus dou xj sigma ij and some body force rho gi. So, substitute. So, what is dou xj of sigma ij? That would be minus dou p dou xj delta ij plus 2 mu dou xj of eij. The first term, which is dou p dou xj delta ij, becomes minus dou p dou xi, because when delta ij acts on dou xj, the j gets replaced with I. For the second term, we need to write down what is eij. So, eij would be half dou ui dou xj dou uj dou xi. As you can see that I have already said here that we are looking at a fluid where mu is a constant. Viscosity is a constant in space. So, the starting point itself was we are looking at a system where the transport coefficient is not a function of spatial coordinate, which is why I took it outside the derivative. So, the second term turns out to be mu. I will have dou square ui dou xj square from the first term, and the second term is going to be dou square uj dou xj dou xi. So, I have taken that divergence and the divergence acts on both the terms. Now, the second term is dou square uj dou xj dou xi. I will commute the derivatives. We are dealing with reasonably straightforward functional forms of velocity. So, on commuting it, I get dou square uj dou xi dou xj, which is dou xi of divergence of u, and that for an incompressible flow is going to be 0. So, this particular term drops off, and finally, we have dou ui dou t plus uj dou ui dou xj minus dou p dou xi plus mu dou square ui dou xj square plus rho gi. This is the statement for momentum conservation, which is to be used in conjunction with the statement of mass conservation. So, for an incompressible flow, these are 3 plus 1. There are 4 equations for the 4 unknown variables. 4 unknown variables, the 3 components of velocity and the single scalar, which is pressure. If you were doing all of this for a compressible scenario, then you would have to look for additional terms, because you remember for the compressible problem, I will have minus p delta ij plus lambda delta ij EMM and then 2 mu Eij. And even if you use the Stokes hypothesis tells us that lambda plus 2 mu by 3 is equal to 0, which means this becomes minus p plus 2 mu by 3 EMM delta ij plus 2 mu Eij. So, with Stokes hypothesis, your stress tensor will have this additional contribution to the isotropic part. So, the isotropic part will have something that will depend on del dot u, a dilatation component that would be there. Divergence of u, you can also refer to it as a dilatation component, that does it expand out or compress in. So, that is going to lead to an isotropic stress. If the fluid could just isotropically expand out, then you would have a corresponding contribution that would arise in the problem. So, this is all for the scenario if it is compressible. So, you can write down the corresponding modified form for the compressible equation, and in the compressible scenario you would have to then go back to your mass conservation and realize that your mass conservation equation is going to take this particular form, the equation of continuity. But that would not be purely sufficient, because you need to assign or you need to give a relation between pressure and density. How is that related? Do you use an ideal gas equation of state, or do you have something more complicated? So, you need additional equation in order to close the whole system, that how is pressure now related to density. So, we will keep our life simpler, because there is enough to learn and do here, which is treating incompressible flows, understanding what incompressible flows actually are. And you can also pose this as, can I arrive at this from the molecular picture itself? So, we discussed this a little bit earlier also, that is there a way by which you can start off by saying that this is all but a bunch of gas molecules. Let us say if you think of it like just like an ideal gas, bunch of gas molecules that are colliding with each other, can I arrive at this equation? So, we went through this in a qualitative manner, and I had mentioned that the picture from where you start off from is what is known as the Boltzmann equation, that gives us what is the probability of finding a molecule at a particular position moving with a particular velocity at an instant of time. This velocity that you see is not the same as the velocity that we are writing down here. The v that I have written down there, that is the velocity of a fluid molecule or a gas molecule. So, they are all not going to move with the same velocity. So, you will have to solve an equation for this, and then from there you can try attempting arriving at this. So, it requires significant again amount of algebra, but eventually you can arrive at this. The point I am trying to make is, from that picture you will have a physical basis of what viscosity is. That what exactly is viscosity? We can solve problems and basically use viscosity and understand that it has this, it is like a frictional kind of quantity. So, before you get formally introduced to fluid mechanics, you have come across this term and you think of it as some kind of a frictional interpretation. But finally, all of these are molecular. It is not necessary that you have a boundary or a wall. If I just have a bulk of fluid, in that bulk fluid, can I understand the concept of viscosity? And one way to think of this, that why this basically arises, is going back to the point of equilibrium, that the fluid system that we are talking about, for which we are deriving these equations, I said it is not in equilibrium. But what I am basically saying here now is that they are slightly away from equilibrium. They are slightly, a little bit departure is there from an equilibrium process, in which case the mu that you have here, the transport coefficient, which we call as viscosity, is related to the velocity fluctuations that are there in at the molecular scale. So, at the scale of these individual molecules, they are constantly, there is a fluctuation that is basically present in the system. So, how much fluctuation do you have from the equilibrium? So, because these are near equilibrium processes that we are thinking, viscosity can be understood as a transport coefficient that captures how much fluctuation is going on in the system. So, there is a molecular interpretation that is there. So, you can come towards this from two directions. You can approach this from a continuum mechanics point of view, where you are making a lot of arguments regarding symmetry, isotropy, etc., and finally you say that it is a quantity that gives you the response of the material in terms of the rate of deformation. You can also arrive at this from a molecular perspective. Nothing to do with continuum mechanics. You start by saying F equal to ma for every individual molecule, and then you say if I average over all the speeds of these molecules, I am basically getting a coarse grained description. So, in doing that, you will at some point need to say a little bit more regarding what is the distribution of these molecules in terms of their speed. How rapidly are they moving? So, if the system was in perfect equilibrium, there is a distribution which is known as the Maxwell-Boltzmann distribution, which in some ways will look like this. I am not writing functional forms etc., but in terms of velocity, or if I am writing here in terms of the speed, the f being the distribution function as a function of speed will look something like this. So, obviously, it is unlikely for you to find something stationary. It is also equally unlikely for you to find something that is moving very rapidly. So, there is a mean, there is a max, there is an RMS velocity, and you try to basically relate this to the temperature of the system, that how much are they fluctuating about the mean in terms of the temperature. Temperature gets higher, they fluctuate more. That is the understanding what we have from kinetic theory. Now, what you are going to say that this f of x comma v comma t, so f will have an equilibrium representation which is the Maxwell-Boltzmann, and then there is a fluctuation of that from that distribution. This is very informally I am writing it down, I am not doing any formalism here, I am just saying that fluid mechanics or what we are writing here as momentum equation can be derived at least for very simple monoatomic ideal gas scenarios by saying that there is a deviation from this equilibrium state. So, when you learn thermodynamics, you are basically talking about equilibrium thermodynamics, and in that particular case your consideration is that the system can be described where every gas molecule is moving with a certain velocity that is given by this equilibrium distribution. Now, when you are doing the non-equilibrium problem, which is a dynamics problem here, or fluid dynamics is what you are doing, they are all connected. So, the same gas molecules where you do PV equal to nRT is the same thing for which you are now doing a dynamics problem, you are writing down a momentum equation. So, it is not like they are different systems. So, when you are doing fluid mechanics, what you are now saying is that the earlier assumption of equilibrium is now relaxed. There is a possibility that they need not follow that equilibrium distribution, and the consequence of them not following that equilibrium distribution is what manifests in one sense in terms of viscosity. So, viscosity is a non-equilibrium quantity, but it is derived from your equilibrium solution by saying that we are slightly away from equilibrium, we are not crazily apart from equilibrium. Now, all that I said here in the last minute or so can be rigorously argued for very dilute non-interacting system, which is an ideal gas. If you say, can I make the same kind of argument for water? The answer is it is nearly impossible. It is very hard to do it because water is not an ideal gas, water is not non-interacting, water is strongly interacting, water is made up of it is a very dense system. But how do we know that we are doing things right? Because at some point you might say, I mean all taken forward, I can take this mathematical equation and just run it through a computer or run it through some very sophisticated mathematical tools and solve it. But there is a need to question it, there is a need to understand that is this true description of reality, and the true description of reality is experiments, observations. So, you make observations based on what this equation describes. You solve this equation, you find a solution, and then you see if it describes reality. And the answer over now more than few centuries to an extent is an overwhelming yes. So, if it was not doing so, all these analysis that we are doing, all the math that we are doing here is pointless. I mean it is a cute problem, it is a nice equation, but it has no connection to reality. So, the equations can be argued from this continuum mechanics principles, but finally how strongly it rests based on reality is observation that you get from experiment, which is why this equation, which is the celebrated Navier-Stokes equation, the reason why it is celebrated is because it gives you a very good description of reality. Reality is not made up of a continuum. Reality is made up of bunch of molecules which are doing things at the molecular level. But if you are trying to understand how you are transporting gas through a pipe, if you are looking at weather, if you are looking at a bucket of water, all of these things can be described by this equation. I mean, incompressibility is a subset we are doing, but broadly speaking, even if you take into account compressibility effects, the Navier-Stokes equation gives you a very accurate description of reality. But it is an approximation, because now when I told you all this from the molecular point of view, you can start becoming more curious and you can say, if it is derived as this small deviation from the equilibrium, what happens when deviations are not small? What happens when deviations become significantly large? Then you are going to get corrections to this equation. Whatever we have written down in this equation is going to be the first description. If you start saying I am pumping gas not through a pipe of millimeter diameter, but through a pipe of few hundred nanometers, then this equation is going to start showing physics which is not consistent with reality. Reality will show something else. So, as you go to very small scales, as you go to cases where the assumptions that are inherently made in terms of arriving at this starts to break down. One more example is a shock. A shock is basically going to be a scenario where mathematically you have a singularity, a discontinuity of quantities. So, when you are basically solving for problems involving shocks, in the vicinity of the shock, the description that you get from this equation is going to be a little spurious. You need to basically then go back to the molecular picture and then do some kind of a stitching, that far away from the shock, I am reasonably good in staying with the Navier-Stokes description, but very close to it, I need to probably go back to the more fundamental molecular picture. So, this kind of tells us now that you can write this in the vectorial form or the tensorial form that we had. So, in the vectorial form, what we had there was a Laplacian. This is your Navier-Stokes equation, abbreviated as NSE. Now, this was a question when we got introduced to Eulerian and Lagrangian description, that in Eulerian and Lagrangian description, why don't we do all of these problems in a Lagrangian point of view? Why is it that we need to actually solve problems in a Eulerian point of view? Because when you write things in an Eulerian point of view, I mean, you are seeing that it is mathematically quite a tedious equation. Now, the Eulerian expression for your conservation is sum of all forces is equal to mass times acceleration, or if I write it in terms of acceleration is equal to sum of all force per unit mass. Now, you can see that the left hand side is your acceleration or density times acceleration. The problem arises with this, I mean, I can have a body force, in which case that is okay. If I have a body force, then body force is precisely in that form. So, if I write rho du dt is equal to rho g, this can be solved in a Lagrangian sense. The problem comes in with the additional terms that you have in your equation. The term that comes from the surface forces, precisely pressure and the viscous component. Because writing this in a Lagrangian coordinate is very painful. This is a pressure gradient. So, at a given point, if you have been doing courses in numerical methods, or you will probably do at some point, you will say that I want to find out the pressure gradient at a particular point. What do? You find out what is the value of pressure in all the neighboring cells and use that to find the value of pressure there, which means that the value of pressure gradient at a particular point cares about the value of pressure in the neighboring location. That is a non-locality in terms of information. The viscous force del square u, once again at a particular location, is a non-local term. It cares about what is the value of the velocity in its neighbor. So, which means when you are doing this in a Lagrangian sense, if the particle were to actually move through, you will have to calculate gradient P and del square u following the fluid trajectory, which is very, very painful. You can formulate it. I am not saying it is not doable. In a formal sense, yes, you can do it. In a formal sense, you can write what is gradient of P as you follow a fluid particle, because gradient P is nothing but dou P dou xi. And then you can apply a transformation which says that as you move along with the fluid particle, what is the pressure gradient as seen by a fluid parcel. As the fluid parcel moves along, it sees different pressure gradient. How do we write that? So, we need to write that pressure gradient and the viscous force in that particular form. So, Lagrangian form of the momentum equations are kind of lost in present day textbooks, but if you want, one very classical book where you will find this is a book by Horace Lamb, which is on titled Hydrodynamics. So, if you are interested in knowing how that equation formally looks like, you can go to Lamb's book and you will find a Lagrangian representation of the equations. So, there are couple of places where you find, but in contemporary textbooks it's almost absent. You won't find a representation of the Lagrangian form. So, before we conclude, there are 3 points I would like to make here. The first point is that I said we have a linear constitutive relation, but the differential equation that we have here, that differential equation is non-linear. So, that is a distinction. The constitutive relation is linear, but the final conservation equation that we have, the Navier-Stokes equation, is non-linear, and the non-linearity precisely comes from the advective term in your acceleration. Now, it is tempting to think that what would happen, or you can just have a thought experiment. What would happen to the world that we live in if it was governed by a fluid that was obeying, let us say, a NSE minus equation, which means Navier-Stokes without nonlinearity. It is a pretty nice equation, right? It is a linear equation, and because it is linear, a lot of things we can do. Now, it is not just about the mathematical difficulty in solving the equation. The question is, a lot of physical phenomena that we see around will cease to exist in absence of the nonlinearity. A simple example, you boil something or you heat something from below. So, this is the bottom temperature which is higher than the top temperature. You heat gas or you heat some fluid, right? You are heating it from the bottom and then it is cooled from the top. Now, if you just say this is governed by my I have not discussed temperature equation, but without getting into the equation of for temperature will obey a conduction equation, and you are going to get a temperature profile which will look something like this. So, at the top you will have the top plate temperature, and at the bottom you will have the bottom plate temperature. Now, if the world was purely governed by NSC minus or the linear Navier-Stokes equation, then in this equation that you will have the fluid acceleration, you will have a pressure gradient, you will have a viscous term, and you will have a body force, where body force is coming from the density variation due to temperature. You can assume a thermal expansion coefficient and say that you change temperature, density changes, which means here you have light fluid and here you have heavy fluid. Now, you keep heating this. If it was purely governed by the linear equations, initially there is no motion. Initially, when you started the problem, you started heating it, there is a temperature profile, there is no velocity that is there. So, u is equal to 0 and the temperature profile, that is some linear function of the vertical coordinate, is a solution, and it will continue to be a solution forever. There will be no change whatsoever to that particular problem. You will have a pressure gradient which is going to balance the density variation in the vertical direction in the momentum equation. So, dou P dou x will balance the rho g, and that is it. There is no motion in the problem. So, you can heat it to an arbitrary temperature gradient and you will continue to get a conduction solution. But in reality, when you do that, after a certain temperature gradient, you are going to actually start seeing that there will be these kinds of circulation cells that it will form. There will be these rolls that will form, and these rolls that are forming is because of this non-linearity that is actually there in the problem. So, that non-linearity is basically what makes that nice conduction problem to become an unstable problem, and it becomes into a convection problem. So, you are transporting then fluid from the bottom to the top. If the nonlinearity was not there, there would be no transport, right? The fluid that stays in the bottom, the light fluid in the bottom stays in the bottom. The heavy fluid that is there in the top stays at the top. There is no way that you are going to get any kind of mixing in the problem, any kind of transport in the problem, which is basically what happens on the surface of the earth. The surface of the earth has a large number of these circulation cells. Obviously, there are details of rotation, etc., that is there, but in a very crude sense, if you didn't have the convective or the advective nonlinearity in your problem, lot of physics that you see around is not going to be there. The only thing that you would have in the entire atmosphere around would be just linear waves that are moving around. There is nothing else that is going to happen. So, habitability and all these things would actually go down. So, before you think of it in terms of a maths problem, it is also important to think in terms of what would the world be that we live in if it was governed hypothetically by a linear version of Navier-Stokes equation. So, with that I will stop here. We will take the Navier-Stokes and then look at various limits of this equation in the next class.